Now, with that said, I want to look quickly at a set of pretend structural drawings so that we can get a better picture of the role of the structural engineer on a project. So here we have a basic steel building that I've put together. Steel superstructure with a concrete foundation and a masonry core around the elevator shaft. So let's browse this pretend structural drawing set. The first page typically will be the general notes page. And this is where the structural engineer provides guidance to the general contractor regarding what type of structural materials to acquire and how to put the building together. So typically one of the first sections you will see is regarding the foundation. And here the structural engineer will provide information such as the soil bearing pressure, frost depth. Frost depth, of course, only applies in areas where the ground freezes. And there will also be a note regarding the grade elevation. Next will be a section on concrete, typically. And here the structural engineer will indicate the minimum compressive strength of the concrete, as well as the weight of the concrete. And this information will also appear in the specifications, and the specifications will control over what appears in the construction documents. But this page more or less serves as a quick reference for the general contractor. Next, there will be a section on structural steel. And here, the structural engineer will provide information for the grade of the steel that is to be used on the project, and also what type of connections, whether it's bolt sizes or types of welds, that the general contractor will be expected to use. Also, with both of these, both concrete and steel, there will be information regarding finishes. Next, there will be a section on masonry. And again, there will be a note indicating the compressive strength of the concrete block, as well as what type of mortar and grout to use between and inside the blocks. Next, if there happens to be any wood on the project, there will be a section on wood. And typically structural engineers won't list the species or types of wood that are required for the project here in the general notes. Instead, they will just say, see specification. And instead, the notes that they will include will be regarding things such as the connections. Wood connections tend to be rather large and cumbersome, so typically structural engineers will provide a note here regarding the connections, telling the contractor to minimize the look of the connection as much as possible. Unless, of course, the design intent from the architect is to have big bulky connections, which is almost never. And one of the last sections for the general notes will be the design input, or the loading criteria. And per IBC Chapter 16, here the structural engineer will provide floor live load data, roof live data, snow load data, wind design data, earthquake design data, And finally, any relevant flood data or other special loads that may not typically appear on a normal project. And so that is just a broad, high-level overview of what you will find on the general notes page of the structural documents. After this page, you will typically find your first set of plans. And so here you can see this first one is the foundation plan. And this foundation plan will have information regarding the concrete foundation, such as the pier size. So here we have P24 listed at pretty much every column location along the exterior. So that P24 indicates that this concrete pier is a 24 by 24 inch pier. Note that these columns do not have piers, as this steel is able to go down into this basement level area and directly down into the concrete. Around the perimeter we have this big, thick concrete retaining wall, and so we aren't able to bring the steel all the way down. So instead we create this little pier pedestal for it to sit on. And these steel columns would terminate at the level above. Underneath the concrete pier tag, we have the concrete footing tab. And note that this is a footing and not a footer. Footer is what goes at the bottom of a document. As with the pier, the number that comes after indicates the dimensions. So this one here would be a 10 foot by 10 foot footing. Also on this plan, you can see that there are some lines, vertical and horizontal, and a tag here noted CJ, and CJ stands for control joint. So as we will discuss in just a minute, concrete expands and contracts, and so we need to provide some areas where it can move, otherwise we will get cracking through the floor slab. Next, moving up to our first level, so this would be at grade, we can see that we have some steel here now. So let's talk about these steel beam tags. So you can see that most of them are W12 by 19. So what does that 12 by 19 stand for? So what does that W12 by 19 tag stand for? So the first letter is going to be the shape. In this case, a wide flange section. And a wide flange more or less looks like this. And it's important to note that this is not an I-beam. An I-beam is actually an older historical shape. So typically what you will see now from steel mills are wide flange sections, and we don't really use or manufacture I-beams anymore. The correct terminology for this shape is wide flange. Next, this number 12 will be the nominal depth of the section. And that word nominal is very, very critical. So if something is indicated as W14, its nominal depth is 14 inches, but its actual depth may be much greater if it is a particularly heavy section. So let's actually look real quick at the AISC shape database. So this Excel spreadsheet is the AISC, or American Institute of Steel Construction, shape database. And you can actually download this spreadsheet yourself from the AISC website, right here. And this document provides all of the dimensions for various steel sizes. So you can see, starting with our wide flange type sections, if I scroll down to the W14s, this W14 by 837 has a depth of 23.6 inches, not even close to 14. But if I scroll down to some of these other sizes, let's say we get to W14 by 99, here you can see we get closer to 14 inches. And in fact, most of these down here are closer to 14 inches. So it's really only the ones with a very high second number here that have a much larger depth. So now let's talk about what that second number is. That second number is the weight of the member. That second number indicates the weight of the member in units of pounds per foot. So this member is 19 pounds per linear foot. Or in other words, this beam here, since it is 20 feet long, weighs 19 pounds per foot times 20 feet equals 380 pounds. So the letter determines the shape, the second number determines the nominal depth, and the third number determines the weight. And nominal does not necessarily indicate actual depth. And for heavy sizes, the depth may actually become greater, much greater than the nominal depth. Typically, these very heavy sizes won't be used as beams, and we'll get into why that is later on in this course. But I still just wanted to make you aware right off the bat that just because you see W14 doesn't guarantee that the shape is only 14 inches deep. Now, what about this third number in the parentheses? What does that indicate? That number is for the number of shear studs. And again, we will get more specifically into what shear studs are in a future video. But basically, they are studs that are welded to the top flange of the beam. So that explains the beam tags. Now let's talk about some of the other numbers that we see here on this plan. We already talked about these numbers earlier. These are the reactions that the structural engineer is providing for the connection designer to use. So the connection between the left side of this beam into this column must be capable of withstanding 65 kips of force. Another tag that we see here is this floor deck tag. And underneath it is this arrow pointing left to right. That arrow indicates the span direction of the floor slab. And here it's important to note that the floor slab is a structural component. And in fact, it's a component for both the gravity system and the lateral system for upper floors. So the floor slab is a structural element. And that's important to note for architects as they push and pull on the floor slab. So floor slabs and edge of slab drawings are typically a very key area for collaboration between architects and engineers. Because ultimately both disciplines have a responsibility for the design of the building's floor slabs. Now let's move on to the second and third floor framing plans. You can see that it's fairly similar to the first floor plan, except now we have a few additional symbols. The first difference I want to point out is these symbols on some of the beams, these triangles. These are indicating moment connections for a moment frame system. And again, we will get more into what that means in a future video. Also, you can see here a dashed line. And this is indicating some type of diagonal member between the floor plans. So if we jump to this elevation view here, we can see that we have some diagonal members going from floor to floor. And finally, moving up to the roof floor plan, we see a very similar layout, except now some of our sizes have gotten a lot lighter. And also, we are now using roof deck instead of floor deck. So that pretty much covers our floor framing plans. And next, we will have the steel column schedule. And this is where the structural engineer will call out the sizes for the columns, as well as the heights, and potentially any locations for column splices. So typically, steel columns will be one long continuous piece, so long as it is around 40 to 50 feet or less. However, if it gets much taller than that, say you have a few more floors added on beyond this roof level, there will likely be some location for a splice. That is, you have two discontinuous members that are either welded or bolted or somehow fashioned together in the field. And the details for those splices, as well as the details for these base plates, will also be given on this page. And next we have our lateral system elevations and details. And here is where the structural engineer will indicate any lateral braced frames or shear walls that are to be designed. And again, we'll talk more specifically about lateral systems in a future video. Next we have foundation details. So here is where we have our retaining wall at the basement level. And finally we have steel details. So up here is the information regarding the floor deck as well as the roof deck. And down below we have a few sections that were cut. So let's talk specifically about this section that I've blocked out. And let's go back to our plan view. So we've cut that section right through this W16 by 26 beam. And so we know that that W16 by 26 has a nominal depth of 16 inches. And if we double check the shape database, we can confirm that a 16 by 26 has an actual depth of 15.7 inches, around 16 inches. We also have the floor deck tag here, and a span direction from left to right. So here I'm going to put up a quick video showing you some roof deck, which is similar to floor deck in its shape. It has this accordion-like configuration. And you can see that as I bend it in this direction, it's very flexible. However, if I try to bend it in the other direction, it's very stiff. And so if we want the load to travel from left to right, we are going to orient it in such a manner that it is stiff in the left to right direction, so that the load is capable of spanning from left to right between the beams. In structural engineering, we use the phrase load follows stiffness. So now we know the size of this beam, we know the shape of the beam, and we know the orientation of the deck. So we have almost all of the information that we need to draw this section accurately. The final bit of information is, of course, the depth of this deck. And for that, we go back to the page that we were on that has the composite slab schedule. And this mark indicates that the total slab thickness will be 6.5 inches and the deck itself will be 2 inches. And so what that means is that the metal deck itself will be 2 inches deep, and then there will be 4.5 inches of concrete poured over top, bringing it to a total thickness of 6.5 inches. So now we can draw this section. So we have our wide flange beam that looks like this. And we have our deck oriented in such a manner that we see the flutes like this. And finally, we have concrete poured on top. And we'll give it a hatch pattern that looks something like this. So this depth of concrete is 4.5 inches. This depth here of the metal deck is 2 inches. And then the depth of the steel shape is 15.7 inches. And so the total structural depth is 4.5 inches plus 2 inches plus 15.7 inches equals 22.2 inches, which is nearly 2 feet. Now, that may be a bit surprising to you that structure would require that much depth, and that's part of the reason why I bring this up at the beginning of the course. Floor-to-floor heights and the depth of the ceiling plenum is something that is crucial for the structural engineer and the architect to work out together early on. And there are many strategies that can be used to reduce the total structural depth, some of which we will be discussing in this course, but it's important to get these issues worked out sooner rather than later. And so it's always best to consult a structural engineer as soon as possible on a project. What you don't want to do is model your entire building with a 6-inch floor plate and then find out that you're actually going to have this gigantic 3-foot beam underneath that you weren't expecting. So that more or less covers the general overview of the roles and responsibilities of the structural engineer, as well as what design output structural engineers put onto their construction documents. And in the next video, we will be focusing more specifically on the types of loads that are on a building, and the design input that structural engineers use.